So we left off in naming amides with the IUPAC nomenclature. So we're gonna follow IUPAC nomenclature for naming the amides, just like we did. Okay, here's our first example. Come here. We look at the carboxylic acid group, and there's 1, 2, 3, 4 carbons. So 4 carbons is butane. So the ending is going to be butane amide. IDE ending. Okay, and here's our nitrogen group, and we have 1 hydrogen and then 1 R group attached to it. So it's going to be N, telling you there's 1 R group attached, and there's 3 carbons, so that's propyl because it's an extension. So it's going to be N-propyl butane amide. Okay, N-propyl butane amide. So again, looking backwards, it tells you it's an amide, which means it's a carbonyl carbon and a nitrogen. And it's butane. There's 4 carbons where the carboxylic acid was derived from. And then the N is the attachment, tells you it's a propyl attachment, which is 3 carbons. And that's how we name it. Right, next one. Again, look at the carboxylic acid group, which is this group right here. And there is 3 carbons. 3 carbons is propyl. So it's propane amide. Drop the E at AMIDE. And we got 1 R group attached. So we have 1 N then. So it's going to be N. And this is 1, 2, 3, 4, 5 carbons, right? 5 carbons is pentane, or in this case, pentyl, because it's an attachment. So this would be N-pentyl propane amide. Okay, N-pentyl propane amide. Okay, same thing again. You look at a carboxylic acid group, and there is 1, 2, 3, 4, 5 carbons. So 5 carbons is pentane. Drop the E, add amide, the word amide. And then we look at our nitrogen group, and we have 1 attachment. So 1 attachment means 1 N group, or 1 N nomenclature. And this is 1, 2, 3, 4, 5 carbons. So it's going to be pentyl. So I put those together, it's N-pentyl pentane amide. Okay. And next one. Okay. Again, we look at our carboxylic acid group. 1, 2, 3, 4, 5, 6 carbons. 6 carbons is hexane. Okay. So we drop the E, add the word amide. And we've got 1 extension. So it's going to be N. Again, if this is a hydrogen over here, then there'd be no N. It'd just be the word amide, and that'd be the end of the word. Okay. If there's 1 attachment, we have 1 N. If there's 2 attachments, if we're 2 R groups, we'd have N on the N comma N. So this is just 1 attachment, and it's 1, 2, 3, 4 carbons. So it's N dash butyl for 4 carbons. So we put those together, it's N-butyl hexane amide. Okay. We got more people joining. We've got up to 5 now. So we're getting there. All right. Any questions so far? These amides, we use them for in medicine. You're going to learn that with the nursing program. We use them as barbiturates. Barbiturates are often called downers. They're derived from amides, and they're used as sedatives. That's what we use to sedate a lot of our patients. Okay. They're also used as anticonvulsants for epileptics. People who suffer a variety of brain disorders manifest themselves in neuroses, anxieties, and tensions. We use barbiturates. Okay. That we use for epileptic behavior when the connection between the brain isn't functioning correctly. These barbiturates settle them down and allow epileptics to not have these seizures and be able to function. Okay. One of the byproducts of this, you'll see if you're working in a nursing home, you'll see we use what's called dilantin. Dilantin's a barbiturate. And when we use it, what it does is causes the patient's gums to grow over their teeth. I wish I should have brought some pictures of that one because it's really amazing. I mean, their gums actually completely, you can't even see their teeth anymore. The gums will grow so much over their teeth. And that's one of the things in treating epilepsy you gotta be careful of with the use of dilantin, called dilantin hyperplasia. And you'll see that in nursing homes, in places where they're using to sedate your patients for you. Okay, that's one you gotta watch out for. And I mean, treatment of it is just to take a diamond burr and just grind off the gums. That's what you do. I mean, it just flies everywhere. It's kind of archaic, but that's how you treat it with the dilatant hyperplasia. Phenacetin and acetaminophen are also amides. Okay, we use those for analgesics. Okay, acetaminophen is an aromatic amide. Remember aromatic? Aromatic means it has a benzene ring attached to it. A lot of medications have benzene rings attached. Okay, it's commonly used in place of aspirin, particularly by people who are allergic to aspirin. You have an ASA allergy, we use acetaminophen. Acetaminophen is what's found in Tylenol. Okay, people who suffer from bleeding ulcers also cannot take aspirin because it's an acid, it's acetylsalicylic acid. Okay, so we use acetaminophen. We use Tylenol. People that are allergic to aspirin or who have bleeding ulcers. It was first synthesized in 1893, acetaminophen. Okay, its active ingredient is in Tylenol and Datril. Okay, so like aspirin, acetaminophen. I'll let my slide catch up here for a second. Okay. Acetaminophen relieves pain and reduces fever. Okay, unlike aspirin, it's not an anti-inflammatory drug though. So acetaminophen, Tylenol relieves your fever and relieves your pain. It's an analgesic, reduces fever and pain, but it is not anti-inflammatory. Aspirin is also anti-inflammatory, reduces the inflammation response associated with it. Phenacetin was synthesized in 1887, okay, used an analgesic for almost a century. Its structures and properties are very similar to acetaminophen. We had some problems with it. Okay, it was banned by the United States Food and Drug Administration in 1983 because of kidney damage and blood disorders that it caused. Now that's the phenacetin. Acetaminophen is very similar and does have those same problems. Acetaminophen has a limit of what you can use it for. Patients that have chronic pain and are on acetaminophen on a regular basis end up with a lot of problems with kidney damage. Lung cancer of the kidney damage, and it ends up being fatal for them. So you still get kidney damage, it's just not in the same dosages anymore. You have to be on it consistently, but we do still get kidney damage with acetaminophen. It's one thing to be careful of giving patients acetaminophen in a nursing setting as a chronic dose of something to help them. And this is what the structures look like. Again, there's your aromatic structure. Okay, your benzene ring, and this is phenacetin, and then this is acetaminophen. And you see the similarities. Okay, you got your carbonyl carbon. This is your amide group right here. And this is the R group. And the only difference is you still have the aromatic compound, which makes it biologically active. But instead of having an ethyl group attached to the oxygen at the end, you have a hydrogen. Okay? That's the only difference between phenacetin and acetaminophen. So this is a lot less kidney toxic, but it still does cause problems. Especially, like I said, if you're working as a nurse in a nursing home, where you're giving persons that medication over and over again, this is something you have to be careful of. Semi-synthetic penicillins. We made a lot of penicillins. Okay? We created them in the lab once we had the discovery that penicillin is an antibiotic. The antibacterial product penicillin was discovered by Alexander Fleming in 1929. It was discovered by mistake, actually. Okay? And once you discover that, then we got some problems with penicillin. Now we make them in the lab, and we get rid of some of those problems. Okay? Natural penicillins produce several species of the mold Penicillium. Okay? It has a number of drawbacks to it. Okay? It's effective only against bacteria referred to as gram-positive. Okay, so penicillin, the original penicillin, was only effective against gram-positive bacteria. So it wasn't a widespread antibiotic. Okay, because of the staining reaction based on the cell wall structures. Remember how penicillin works? Human cells have cell membranes, and they do not have cell walls. Bacterial cells have cell membranes and a cell wall around it. Penicillin kills or punch holes in that cell wall. Okay, human cells don't have a cell wall, so it doesn't affect human cells, but it affects bacteria cells. It punches holes in the cell walls by inhibiting one of the structures that is incorporated in the cell walls, and then the bacteria dies because the cell wall leaks. Okay, they're also very susceptible to destruction by bacterial enzyme called beta-lactamases, and some were destroyed by stomach acids, had to be administered by injection. Okay, so we're getting resistant bacteria to a lot of the penicillins now. Okay, as long as the bacterial enzyme, if the bacteria contains what's called beta-lactamase, it will destroy the penicillin. The penicillin will not kill the bacteria. Okay, And a lot of penicillin is destroyed in the stomach by the acid content. So you can't take it orally. We've modified things that so now we can take it orally. But the original penicillin had to be injected because it was destroyed by the stomach acid. Overcome these problems, chemists have produced semi-synthetic penicillins, which use the original penicillin as a starting point, and then we add or modify the R groups attached to it. So we have the main structure that's biologically active, and all we're going to do now is modify the groups that hang on to that main structure. And that can make it resistant to acid. So you can take it orally, like Pen-VK can be taken orally. Okay, penicillin, Pen-G, penicillin is given IV. Okay, so depending how we modify it, we can get drugs to do different things. And that's what organic chemistry is all about. Okay, to modify drugs so they can be used. So the core penicillin was called 6-amino penicillinatic acid. It consists of a thiazole ring, so it has a sulfur enzyme in it, and it's fused to a beta-lactam ring. Okay, there's an R group that's bonded to an amide bond to its core structure. So here's your ring structure right here. Okay, it's a double ring. There's your thiazole for your sulfur, and here's your amide. Okay, your carboxylic acid. Okay, this R group here, that's what we change. That's the difference between ampicillin, amoxicillin, penicillin G, penicillin VK. What we're changing is this is the active biological part of the molecule here. That doesn't change. We're changing this functional group right here, this R group, to make it and give it different properties which we want. Okay, so 6-amino penicillinic acid. So here's your beta-lactam ring. This ring here, this first ring is your beta-lactam ring. This one is your thiazolidine ring with a sulfur group attached to it. Okay, this is the site of amidase attack. This is where you break the amide bond right in here. Okay, so the beta-lactam ring confers the antimicrobial properties. That's the part that destroys the cell membrane. Okay, the R group determines the degree of antibacterial activity, the pharmacological properties, including the type of bacteria against which it is active, and the degree of resistance to the beta-lactamase exhibited by particular penicillin antibiotic. So if we change that R group, we can change the resistance to the penicillin that we're giving. Okay? You got to remember, bacteria evolve extremely fast. I mean, we're not waiting generations like we do with humans for another generation. Bacteria replicate every several minutes or so. So their generations occur very quickly. So they can evolve resistance to antibiotics, and they do it very quickly. And we're using antibiotics. In our society, we use antibiotics. We overprescribe antibiotics. If someone comes into the physician's office, into your clinic, into your emergency room, if they've got a cold, they got a virus, antibiotics do no good. But patients want to have medication. They want to think that you're getting something, so doctors usually prescribe antibiotics for them. Okay, because of this way of prescribing it, we've decreased the effectiveness of it. Because the more we prescribe it, the more it's being exposed out there, and the more the bacteria are evolving against these antibiotics. So they're not starting to work. And we're getting what's called super infections or nosocomial infections in the hospitals that we can't treat anymore. And we give antibiotics to cattle to keep them healthy. And all these bacteria are doing is we're exposing the evolutionary trait of these things. They evolve to be so they are not susceptible to these antibiotics anymore. And it is turning into a big problem. Okay, there are properties that must be modified to produce penicillins that are acid resistant, so you can take it orally. I mean, it's so much more convenient to take a drug orally than to give an injection of it. Okay, in fact, you want a broad spectrum rather than just gram-positive bacteria. You want to create gram-negative. You want to affect spirochetes. You want to affect all the different kinds of bacteria that you can. And beta-lactamase resistance. You want to make sure that the bacteria is not resistant to the antibiotic you're using anymore. Okay, so what we do, we remove the natural R group, okay, by cleaving the amide bond with an amidase. So we cleave right where that amide was, that R, that carbonyl carbon. Okay, then you replace the R group and then test it. See what it works on. Put it in a petri dish, stick it in there with bacteria and see what it does. See if the bacteria is resistant to it, and we check it. We check out how it's resistant to acid resolving. You can see it can be taken orally. Okay. The resulting semi-synthetic penicillins, we have made ampicillin, methicillin, and oxacillin. And all we're doing is replacing that R group. We're keeping the biologically active portion the same, and we're replacing that natural R group to give us the different things that we can use to our advantage. Okay, and these are the different R groups that we've been replacing. You can see this is ampicillin, and now this is where the bond was cleaved. This is your carbonyl carbon and your nitrogen, and this is the R group right here that we added. For methicillin, this is the R group that we added. And for oxacillin, this is the R group that we've added. So you can see our biologically active portion, which is the ring structure here, the beta-lactam ring and the thiazole ring, okay, are all stayed the same. So biology is still going to be an antibiotic. It's still going to kill what we want it to, but now we can change its spectrum. We can change whether we can take it orally or not, and we can change the resistance to it from the bacteria by modifying the R group on the end. Reactions involving amides. Now we're going to react these things. Okay, how we prepare amides. Remember, it's a combination of a carboxylic acid and an amine. Okay, so primary and secondary amines react with acid chlorides. Remember, we made acid chlorides by adding chlorine to a carboxylic acid. Okay, and acid anhydrides to produce amides. Okay, and you got to remember that we use a hydrogen because we cause a lysis reaction. We get rid of water. We get H and OH. So you have to have an H to get rid of. So a tertiary amine cannot form an amide because you have to have that hydrogen to form with water in the hydrolysis reaction. So only primary and secondary amines can react to form amides with acid chlorides. And 2 molar equivalents of the nitrogen source are required. So you can make 2 ones and you can put a byproduct of it. Okay, you need 2 moles equivalencies for your nitrogen source in the reaction. They're acyl group transfer. You're transferring an R group from one to another. And here's the basic reaction. Okay, here's your acid chloride. Remember how we made those? Okay, and then 2 of your amines, a primary or secondary amine. Okay, the Cl is put over here with another this because of the hydrogen, and the NH2, so that CH, the Cl is transferred off. Okay, and the NH3 comes here, then one of the hydrogens comes off of here, bonds to the NH4 to produce an ammonium chloride. So basically the nitrogen is forming a new bond here after the chlorine is being kicked off, and then one of the extra hydrogens are coming to form an ammonium chloride plus your amide. Okay, so your acid chloride reacts with 2 molar ammonia or amine, okay, to produce an amide and an ammonium chloride, or an alkyl chloride, depending if it was an R group on there. Okay, so acid chloride is made from carboxylic acids by reaction like PCl5, PCl3, SOCl2. Any of those will react with the carboxylic acid to produce the acid chloride. Okay. Amides are made from these acid chlorides, which are derivatives of carboxylic acid. That's where the carbonyl group comes from. Okay. So this is our carboxylic acid. This is a review from last time. Reacts, like I said, PCl5, PCl3, SOCl2, any of those as a catalyst, and it's going to produce your RCOL, so your acid chloride and other inorganic products. Okay, you need 2 molar equivalents of the amine for the reaction to occur. Okay, so you have this R group. So here's your acid chloride. If the chloride was transferred off, you need 2 nitrogen sources, whatever it is. 2 molecules you have to add to that, because one's going to form the ammonium chloride or the acyl chloride, and the other is going to form the amide group, amide functional group. Why did that lock up on me? Okay, let's see if this one locks up again. It's still locking up for some reason. Doesn't like, oh, there we go. It just started. Why is it giving me so much trouble on that one slide? Okay, so you need 2 molar equivalents of the amine of the nitrogen source. Okay. Okay, so the HCl is transferred from the acid chloride from the Cl atom of the nitrogen atom of one ammonium or the ammonium molecule. The second ammonium reacts with the NaCl, the HCl formed hydrochloric acid to produce the ammonium chloride or alkyl ammonium chloride. So you're going to produce 2 things. You're going to produce the amide, okay, and you're going to produce the ammonium chloride. And it's going to take 2 molecules for 2 nitrogen sources. So the reaction between butanoyl chloride and methanamine to produce N-methylbutanamide is an example of a acyl group transfer reaction. Okay, so this is butanoyl chloride. Butane is 4 carbons, and the oil chloride means it's a carboxylic acid. The O is replaced with the Cl. So this is butanoyl chloride, and you should react with 2 methylamines. Okay, so here's your methylamine. This is a methyl group. That's right here. Okay, and this is your butyl group right there. Okay, and your other another nitrogen compound goes here to give you your acyl chloride. Okay, so we're breaking this up. Let me get these out of the way so you can see it here. Okay, this is your butanoyl chloride. So you're transferring this chlorine, okay, up to form HCl. Okay, so one of the hydrogens comes up from here, form HCl. Okay, the other one's going to form here. This nitrogen is going to bond there. So you're going to get the nitrogen, CH3. Okay, and then the HCl is going to react with the other one to give you your CH3, NH3, the Cl minus, and the H plus. Okay, because this breaks apart right in here. So this gives you your extra H here, and then your Cl minus. So there's your butanoyl chloride, methanamine, N-methylbutanamide, and your methyl ammonium chloride. Okay, so the reaction between an amide and acid anhydride is also the same kind of transfer. Okay, general equation is the same thing. This is your acid anhydride. Again, you need 2 nitrogen sources. Okay, so the nitrogen is going to bond directly to the carbon here, and you're going to get your R, C, double bond O, okay, and that's going to form your NH2 that you have right here. Okay, that hydrogen is going to react, put an OH group here. So this is going to become OH from this extra hydrogen right here. Okay. And then you're going to form the H is going to transfer to the second molecule to give you NH4 plus, and it takes the hydrogen off of the carboxylic acid. So this is your acid anhydride. This is ammonia. That's your amine, and it forms an amide and a carboxylic acid salt. I'm having so much trouble. I think the internet thing is giving me trouble up here. So when subject to heat, the ammonium salt loses a water molecule to produce a second amide molecule. Okay. So the amide bond and artificial sweeteners. We're talking about artificial sweeteners a little bit here. If we look at the amide bond, here's your amide bond again, your carbonyl group here, and your NH. This is aspartame. Okay. Aspartame and neotame are the 2 artificial sweeteners. Aspartame is aspartic acid and phenylalanine. Those are the 2 amino acids joined by the amide bond. Okay. Okay. Neotame is your modified aspartic acid and phenylalanine. So those are 2 different artificial sweeteners that we created. Okay. NutraSweet. NutraSweet is the dipeptide aspartame. Okay. Neotame is a newly approved sweetener that came on the market, and it's also a dipeptide. There's 2 amino acids, so it's a dipeptide. Okay. One of the amino acids modified, so it's safe for use by phenylketonuria. Patients that have phenylketonuria, they lack the enzyme to process the amino acid phenylalanine. So you have to restrict their diets to the amount of phenylalanine the body can use. There's no extra phenylalanine. Now, if they use this, they can't use sweeteners. They can't eat certain types of sweets. Can't hardly any sweets. But now with the modification that we use for Neotame, instead of aspartame, okay, for aspartame they use aspartic acid and the phenylalanine. Now for Neotame we use a modified aspartic acid and the phenylalanine. This modification, see the difference? This has NH3 group here. This is this huge group here. That huge group they put on there blocks the phenylalanine from building up in the body, becoming toxic. Okay, so it doesn't allow it to function in there. So this is safe for your patients that are phenylketonuria, have phenylketonuria. Okay, so packets of aspartame can carry the warning label. Phenylketonuria contains phenylalanine. Anything that contains phenylalanine, they have to be very careful about. They only eat a certain amount. Digestion of aspartame and heating to high temperatures during cooking breaks both the ester bonds and the amide bond, releases amino acid phenylalanine. And that's why they can't have it. People with genetic disorder, phenylketonuria, or PKU disease, cannot metabolize this amino acid. Okay. As a result, it builds up toxic levels that cause mental retardation in an infant that's born with this condition. And now every day in the United States, everyone born in the United States is checked for PKU. Everybody born. Okay? Because it's such a deadly disease and we weren't aware of it, didn't know what was causing it. Okay, it's no longer occurs because every child that is born is tested for PKU at the time of birth. Okay, and each is treated, if it has positive for phenylketonuria, is treated with a diet that limits the amount of phenylalanine to only the amount required for normal growth. It doesn't develop extra in the body. In July 2002, the Food and Drug Administration approved a new artificial sweetener that is related to aspartame called Neotame. Right? It has the same core structure as aspartame, but a 3,3-dimethyl-butyl group has been added to the aspartic acid. That was that big group dimethyl-butyl that we saw. 4 carbons with the number 3 position is 2 more methyl groups on top of that. Okay. Digestion and heating still causes breakage of the ester bond, but that big bulky portion there, that 3,3-dimethyl-butyl group, blocks the breakage of the amide bond. So now the amide bond is not broken. So you're not releasing phenylalanine into the body. So it blocks that breakage of that bond. So Neotame can be used without risk, people do PKU, and also retain its sweetness during cooking. Okay, what is the structure of the amine? That on reaction with the acid chlorides, so we'll give each of the following products. So look at the top reaction. What are you gonna have to react it with to form the following product? All right, here's your acid chloride, ethanoyl chloride. There's 2 carbons here. So this portion here is that right there. Okay, so what's reacted with came up with N, hydrogen, hydrogen, and 1 carbon. Okay, because this hydrogen gets transferred with the Cl and this N bonds to right there. And you get the NHCH3. And you need 2 of these, 1 for your amide and 1 for your ammonium chloride, or your methyl ammonium chloride in this case. Okay, makes sense. So that's the starting materials for the first one. So the first one is 2 CH3 NH2s, just what we drew there. Look at the second one. Okay, this is our acid chloride, and our acid chloride is, where's our acid chloride here? CH3, CH2, CH2. So here's your acid chloride. right there. That's this group right here, right? Here's your acid chloride. So what are we adding to it to form an amide? We're adding dimethyl groups to it, right? So we're adding a CH3, and an H. And we need 2 of those. Remember that H is going to react with the chlorine to produce your ammonium chloride over here. You need 2 of those to perform your ammonium chloride. Okay. So this is a compound we need. We need an NHCH3 twice. So CH3 twice, N8. This is exactly what we're starting with. That's what we need to start with. We need 2 of them. Okay. And what are the structures of the acid chlorides and the amines that we react to give each of the following products? So look at the products. N-ethyl hexamide. Okay, so we should be able to draw that. Okay. Again, organic chemistry, big thing you must have learned this semester so far is work backwards. So we have hexanamide. So we have 6 carbons, and it's going to be an amide bond. So hexanamide, you're going to have 6 carbons. So it'd be 1, 2, 3, 4, 5, 6 carbons. Okay, hexane and N. There's your nitrogen. And we have 1 attachment that's an ethyl group and a hydrogen. That's N-ethyl hexane amide. So what do we need to start with? What's our starting materials to produce that product? We've got to start with the acid chloride, which is going to be the same thing here, CH3. Well, these are all hydrogens here, CH3, CH2, 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 CH2. So that was 1, 2, 3, 4, 5, 6 carbons, carbonyl group, and our chloride. That's our acid chloride that we need to start with. And then the amine is going to be 2 hydrogens and an ethyl group. Those are starting products. Okay, this looks a little bit much clearer than I can draw it. So then this is our, we drew this first, right? That is N-ethyl hexane amide. We drew that first. And then we noticed this part comes from our acid chloride. So this is our starting chloride, hexanoyl chloride. And then this part, remember it has to lose a hydrogen, is CH2, that's an ethyl group. So it has to be an ethyl group with 2 hydrogens on it. And it takes 2 of them. Those are our starting materials. That's how we get it from that. And then the byproduct is also going to be the ethyl ammonium chloride with the Cl, the HCl added that was driven off from the first reaction to produce the first product that we have. Remember, it takes 2 nitrogen sources, 2 molecules, molar equivalents. All right. And propylbutanamide. So the key to any of these is to being able to draw the product. So working backwards, butanamide, butane is 4 carbons, right? And it's an amide. So you have 4 carbons. There's your double bond oxygen. There's your N. And it says N-propyl. So there's CH2, CH2, CH3, propane, and a hydrogen. So then you break that apart. You have 4 carbons and your chloride. And then you have 2 nitrogens and your propyl group. Okay, like I said, I can't write as neat as this here. So here is N-propylbutanamide. This is what you would write. And to know what you start with, you just look at this. You break it into your carboxylic acid group, which would be right here. And then you make that and you put the chlorine on the end of it. That's your acid chloride. That's what reacts. Okay. The next one is the the ammonia group, and he takes two of those. Remember, he had two nitrogen sources. Okay. Remember, you lost a Cl from this one here, and you lost a hydrogen from this one here. So we add our hydrogen back onto this, and we get propyl extension on that. So ammonia, propylamine. Okay, there's our one extension on that, and then our ammonium chloride byproduct. Okay, hydrolysis of amides. Amides hydrolyze with a strong acid to produce a carboxylic acid and an alkyl ammonium ion. So if you have two different R groups, we have our acid. Okay, we can break the bond. Hydrolysis is adding water. So OH to one side of the bond, H to the other side of the bond. We're adding water to it. That's what we're doing. So we break the amide bond, and we have our carboxylic acid, and we have our amine. Right? Adding water, H and OH, one to each side of the bond, as that bond splits. So there's your amide, strong acid, goes to your carboxylic acid and your amine, or your alkyl ammonium ion in this case. Okay, a strong base. So this was a strong acid. A strong base produces a carboxylic acid salt and an amine. So here's your strong base, sodium hydroxide. And again, we split the same thing. We're going to break this amide bond. Okay, the OH is going to go to form your carboxylic acid, but now you got a base. So the carboxylic acid is donate that hydrogen back again to the amine group, and you get your Na plus. So you formed your acid. As an intermediate step, you formed RCOOH, and then it lost that hydrogen because it's in a basic solution. Remember, acids donate protons, bases accept them. So it donates its proton because it's in a basic solution, and it forms the carboxylic acid salt. Okay, opposite charge attract. There's the carboxylic acid is the negative charge. The metal of the salt is a positive charge, and it's going to form the amine. Okay, so it all depends on whether it's an acid environment or a basic environment where the charge is going to be. If it's an acidic environment, you're going to have the carboxylic acid, and you're going to have the ammonium absorbing the H plus. Because remember, amines are bases. Right? So they're gonna attach or absorb the hydrogen, and the acid is gonna keep it on. Okay, if it's in a basic, the H is gonna be pulled off the carboxylic acid, resulting in a carboxylic acid salt, and then the amine. So basically, in a strong acid, the ammonium gets the charge, plus and the minus. In a strong base, the carboxylic acid has a charge on it because it's donated its proton. So there's your amide, there's your strong base, there's your carboxylic acid salt, and your amine. All right, so these are just examples of the same thing here. Butanamide, strong acid. Remember, strong acid breaks this bond. Okay, you're going to add water. You're going to have OH and H. Okay, so you're going to end up with your carboxylic acid and you're going to have the ammonia, which is NH3, and the extra H here is going to form it to form ammonium. So you go from butanamide to butanoic acid. Okay. So remember, when you're in a strong acid, okay, you have a strong acid here, this carboxylic acid is going to keep its proton on. And the extra proton from the acid is going to attach to the base here, which was ammonia, and it's going to form ammonium ion. Okay. When it's in a strong base, you still break the same bond, and instead of forming the OH, the H now gets protonated. So there's your carboxylic acid and your salt, the middle part of the salt. and then the rest of the amine is going to form, the NH2CH3. Okay. So it all depends whether you're in acidic or basic solution, where the ion is going to form. So with acidic solution, the ion forms on the ammonium compound, the nitrogen compound. In a basic solution, the ion is going to form on the carboxylic acid portion of it, because it's going to donate its proton to the base, and vice versa for the other one. Okay. So preview amino acids, proteins, and protein synthesis. We're going to get into a lot of this in the next following chapters in biochemistry. So a protein is a polymer, which is many links of amino acids linked by the amide bond. So every protein in our body is just a link of 20 different amino acids, and the combination it provides for that protein. Okay. So the amino acids are going to link together by an amide bond. As the amino groups and the carboxyl groups link, water is lost. So you take H and OH between those two bonds, and we form the amide bond. So the peptide bond, that's referred to a polypeptide chain, your proteins, is an amine bond. This is the amine bond right here between the carbonyl group and the nitrogen. This is your amide bond. Okay. That's what links all the amino acids together. We're getting into transfer RNA, how it comes out, and it reads it by the ribosomes come out, and they read each unit, and they basically staple on another amino acid, and it forms a peptide bond by removing water between those two groups, between the amino acid and the next one that's put onto it. Okay. So protein synthesis uses what's called transfer RNA, tRNA. So alpha amino acids are attached to transfer RNA molecules, abbreviated tRNA. The acyl group and the amino acids are transferred to the nitrogen, another amino acid, to form the peptide or the amide bond. Same thing, the amide bond is the peptide bond. It's what's linking these peptides together to form this polypeptide chain of this protein. Okay. So here's your transfer RNA. Okay. Your amide bond is going to link this right here. And this is an alpha amino acid. Okay. All amino acids are going to have this structure here. The R group is what gives each individual amino acid its individuality. Like I said, there are 20 amino acids. The only difference between the amino acid is the R group. And if you look at the R group, remember how we label alpha, beta, delta, gamma in the Greek alphabet? When we labeled one for common names, I told you that's the part I want you to remember. You don't need to memorize all the other rest of it, but I want you to know when you're numbering for the Greek letters, alpha, beta, delta, gamma, epsilon, etc. Okay, the alpha carbon is the first one after the carbonyl carbon. And then alpha, the next one after that would be the beta if there wasn't a carbon there, and so on. Okay, but the alpha carbon is the carbon after or adjacent to the carbonyl carbon. The R group is attached to the alpha carbon. That's why these are called alpha amino acids, because the R group attaches to the alpha carbon of the amino acid. Okay, so amino acids have the basic structure NH2. Let me just draw it here and we'll show you. And we'll get into this a little more. And there's a hydrogen here, and this is your R group. So there's your amino acid. So again, this is your carbonyl carbon. This is your alpha carbon. So that is where the R groups differ there. That's really called alpha amino acids, because that R group attaches to the alpha carbon, and that's the only difference in the different amino acids is the R group. So the alpha amino acid is a carboxylic acid with an amino group on the alpha carbon to the carboxylic acid, the carbon adjacent to the carbonyl carbon. Okay, the alpha carbon has an R group side chain, except for glycine. Glycine is the only amino acid where the R group is a hydrogen. It's not another carbon group. So instead of an R group there, it has a hydrogen. So there's two hydrogen in that case, and that's glycine. Everything else has a different R group, different type attached to it. And this is a great picture of it. At physiological pH, which means it's a slightly basic solution, okay, it's going to lose its proton, and this is going to lose a proton. This side is going to accept a proton. These are called what's called zwitteron ions. They have a positive charge and a negative charge inside the same ion. Again, this is your carbonyl group. So this here is your alpha carbon. Okay, carbon adjacent to the carbonyl group is your alpha carbon. And at the alpha carbon is where you're going to have your R group attached. Neurotransmitters. Neurotransmitters rely on our nervous system to transmit information across our axons, our nerves. Neurotransmitter carries signals from a nerve cell to a target cell, or either another nerve cell or muscle cell. So in other words, when there's we're doing a lot of this in anatomy this last week, the whole nervous system. When there's a stimulus, it has to travel along nerves in the body for a reaction to occur. I mean, think about it. It has to travel both ways. You have to come in and come out. So if you put your hand on a hot surface, that stimulus has to go into the brain. So you have to have neurotransmitters that allow that nerve impulse to travel along your arm, up in your spinal cord, up your brainstem, into your brain. Now, once in the brain has to decide what it wants to do about it. And if it's hot enough, the brain wants to move it. So now it sends information back down the arm, down the brain, down through the brain, down to the brainstem, down to the relays, down to the arm, and then you move your hand. Okay? All this occurs because of neurotransmitters. That information from one nerve to the next has to be transferred along a line. And what we use for that is what's called neurotransmitters. Oops. How do I get rid of this? There we go. Okay. They can be excitatory or inhibitory. They can cause a reaction to occur, or they can cause a reaction not occur. If you put your feet in the jacuzzi, you got that information coming in that the water's nice and warm, they inhibit any reaction. They leave the feet in there. It feels good to the body, okay? So it can be either excite to happen or it can stop the neuron from firing, okay? They all contain nitrogen. Every single neurotransmitter contains nitrogen. And they're catecholamines. Catecholamines include dopamine, epinephrine, and norepinephrine. Those are three of your neurotransmitters, okay? They are all synthesized from the amino acid tyrosine. So dopamine, epinephrine, and norepinephrine all come from the same one amino acid, tyrosine. Okay. A deficiency in dopamine, if dopamine is in deficient quantities in their body, that results in Parkinson's disease. That's what causes Parkinson's. Okay. Is a decrease in the body. So you think you just give the patient dopamine and that would fix the Parkinson's. No, it doesn't work like that, because dopamine cannot cross what's called the blood-brain barrier, but we'll get into just a second here. Too much dopamine is associated with schizophrenia. So too little dopamine, you get Parkinson's. Too much dopamine, you get schizophrenia. Okay, so you want just the right amount of dopamine in your body. Okay, dopamine is critical to good health, which you can see. Okay, a deficiency in the neurotransmitter dopamine results in Parkinson's disease, which is characterized by tremors, monotonous speech, loss of memory, problem-solving ability, and loss of motor function. Right? It would seem logical to treat Parkinson's disease with dopamine, but you can't do that. Dopamine cannot cross the blood-brain barrier to enter the brain cells. In other words, dopamine is a neurotransmitter inside the brain. Okay? If you take dopamine, it doesn't get to the brain because the brain has what's called a blood-brain barrier, and it prevents things from getting to the brain that doesn't belong there, or the body doesn't want there. So it blocks things from entering it. Okay, that's why the difference between heroin and morphine. Okay, morphine does not work in the body. I mean, it sounds funny, but I'm sorry, I said that better. Heroin does not have any effect on the body. Heroin has to be converted into morphine. The morphine receptors are real similar to our endorphin receptors. So morphine bonds and gives you that feeling of being high, or that pain relieving feeling. Okay, so morphine works in the body. Heroin has no effect on the body. It has to be converted to morphine to work. Okay, so you would figure morphine would be more quicker response, but it's not. Heroin responds much quicker. They didn't experiment with rats. Okay, they took rats, we injected heroin, and we injected morphine at the same time. Okay, counted 15 seconds and cut their heads off. So we stopped the morphine and the heroin from moving into the brain. The heroin has concentrated tremendously in the brain. Heroin passes the blood-brain barrier. Once it's there, it gets converted to morphine and acts very quickly on the brain. So heroin is extremely more addictive because it works so much quicker because you have much factor high because it crosses the blood-brain barrier. So even though it's got to get converted to morphine, it crosses the blood-brain barrier first, then gets converted to morphine, and then does action. So that's why heroin's much more addictive than morphine. So this blood-brain barrier has special cells that allow certain things to pass and other ones not to. So that's why you can't treat Parkinson's with dopamine, because dopamine will not cross the blood-brain barrier and get into the brain cells. Okay? In the brain, dopamine is synthesized to what's called L-DOPA. Okay, we'll get into DNL isomers in the next chapter here, too, in chapter 16, which is really interesting for a lot of drugs. L-DOPA can cross the blood-brain barrier. Okay, L-DOPA is what we use to treat Parkinson's disease. It crosses the blood-brain barrier, and the L-DOPA, okay, is one of the products of dopamine that allows it to work as a neurotransmitter. So just as too little dopamine causes Parkinson's, too much it causes schizophrenia. It's gotta be you got to worry about the doses you give on that. Dopamine also appears to play a role in addictive behaviors. People who are addicted to certain things, Diet Coke, for example, cigarettes, heroin, morphine. It's because of the receptors of dopamine in the brain that are causing it. They cause addictive personalities or addictive behaviors. In proper amounts, it causes a pleasant, satisfied feeling. Yes. My wife likes her Diet Cokes. The greater the amount of dopamine, the more intense the sensation or the high that you get from the product that's producing dopamine. Okay. Several drugs have shown to increase the levels of dopamine. That's what causes addictions. If you increase a pleasant feeling in the brain, that's going to cause an addiction because people like pleasant feelings. Okay. Among these are cocaine, heroin, amphetamines, alcohol, and nicotine. All those are very addictive drugs. And every one of those causes an increased level of dopamine, which is a neurotransmitter in the brain. Okay. Marijuana also causes an increase in brain dopamine. That raises the possibility too that has potentially produced addiction. Now, a lot of people say marijuana is not addicting, but anything that can produce a satisfying feeling in your brain with the release of dopamine can cause an addiction. Okay. Now, epinephrine, which is adrenaline, which everybody knows what an adrenaline rush is. Okay, epinephrine and adrenaline are both involved in the fight or flight response. That's when your body gets keyed up to either run or fight. Okay, it's got to get keyed to one or the other. Epinephrine stimulates the breakdown of glycogen and it produces glucose. Glucose is metabolized to produce energy for the body. Energy can be used to fight or to run or to fight. Okay, so epinephrine is the other neurotransmitter. Norepinephrine is involved with the central nervous system in the stimulation of other glands and constriction of blood vessels. Okay. A little lower, where you can hear. No, not the light, the book. Okay. So norepinephrine is involved with the central nervous system and the stimulation of other glands and constricts your blood vessels. So it's the body ready to fight the fight or flight response. Okay. All these responses for the body to meet the stressful situation. Okay. It's what the body does by releasing these neurotransmitters. Okay, the pathway of catecholamine synthesis. All right, let's take this. All right, so this is tyrosine. Remember we said tyrosine is the starting point for all the neurotransmitters, norepinephrine, epinephrine, and dopamine. So this is tyrosine. This is your amino acids, your alpha amino acid. Here's your NH3 group, your carboxylic acid group. Here's your alpha carbon. Here's your hydrogen. And this is your R group. Just a little bit lower, the book part. Hold on a second. Okay, there's a tyrosine. And then tyrosine is converted into what's called L-DOPA, which we talked about. And L-DOPA just adds another OH group onto the aromatic ring. Okay. Then L-DOPA gets converted into dopamine in the brain. Modification of the R group again. You can see. And then dopamine gets converted into norepinephrine. Okay. Norepinephrine gets converted into epinephrine, which is adrenaline. So dopamine, okay, is a synthesis of a tyrosine, synthesizes dopamine, norepinephrine, and epinephrine in the brain. Okay, and this is the pathway that catecholamine synthesis. This is your starting point, tyrosine, converts to L-DOPA, dopamine, norepinephrine, and epinephrine, which is adrenaline. Okay, and all it's doing is modifying of the R group of the amino acid. Okay, serotonin. Serotonin is a neurotransmitter made from what's called tryptophan. Tryptophan is another amino acid. Okay, deficiencies associated with depression. Okay, so deficiencies of serotonin are associated with depression. Okay, possibly involved with carbohydrate cravings. Okay, so it also causes depression in the body and causes you to crave carbohydrates. Okay, serotonin affects the perception of pain, thermal regulation, and sleep. Okay, so this is tryptophan. Tryptophan goes through an intermediate product and then produces serotonin. Okay, so serotonin is your neurotransmitter, converted from tryptophan. And again, it's an alpha amino acid. Here's your carboxylic acid group. Here's your ammonia group. Here's your hydrogen. And this is your alpha carbon right here. And attached to the alpha carbon is your R group. And this is the R group for tryptophan. Again, there's 20 amino acids in the human body, and each one has a different R group that's attached. That's what makes them different. So a deficiency of serotonin has been associated with depression. We proved that clinically. It's also thought to be involved in bulimia and anorexia nervosa, okay, as well as the carbohydrate cravings that characterize seasonal affective disorders. It was called SAD. Seasonal affective disorders, depression is caused by a decrease in daylight, like during the autumn and winter when there's no sunlight. We get what's called seasonal affective disorder, where you get depression caused by lack of sunlight. Okay, it's thought to be involved with the serotonin neurotransmitter. Serotonin affects the perception of pain, thermoregulation, and sleep, like we said. Okay. There are those who believe that a glass of warm milk will help you fall asleep. Okay, warm milk contains tryptophan. Okay, you know how sleepy you come after a big Thanksgiving dinner? Turkey. Turkey contains tryptophan. Can turn that one down, book part. Let's turn it down a little bit. Thanks. Okay, you know how you become sleepy after Thanksgiving dinner, you have that turkey? Those both contain tryptophan. Both milk protein and turkey are very high in tryptophan, and those produce serotonin. Serotonin makes you sleepy. That's why after a big Thanksgiving dinner, you get sleepy and get your rest. All right, Prozac. Prozac is one of the newer generation of antidepressant drugs, one of the most widely prescribed drugs in the United States. Okay. Prozac is a member of the drugs called selective serotonin reuptake inhibitors. So it's an SSRI drug. It's selective serotonin reuptake inhibitors. Okay. So what it does, it inhibits the reuptake of serotonin. So Prozac effectively increases the levels of serotonin because it's not allowing the body to take it back up. So it's increasing the levels of it. Okay, it relieves the symptoms of depression that way. It keeps the levels of serotonin high so that a deficiency of it does not occur, and it gets rid of the depression. So it keeps you more on an even keel that way. Okay, and this is Prozac with the three fluorine groups attached to a carbon in the center. And again, you have your benzene rings and then your nitrogen compound. Opiates, opiate biosynthesis in the mutant poppy for making heroin. Okay. We'll go another 10, 7, 10, 11. There's 8, 11 here in Utah. All right, 7, 11, we'll take a break about 10 minutes. So the opiate biosynthesis in the mutant poppy. Okay, Hippocrates Father Maunus was the first recorded record of therapeutics of opium in 460 BC. So they knew about therapeutic effects of morphine and of different opiates back then. Okay. Although not recorded, it's probably true that the addictive properties of opium were recognized soon after that. Once you start using it, you realize it becomes addictive. Okay. The opium poppy is cultivated legally and illegally in many parts of the world. Okay. Flowers vary in color from white to a deep red, but the seed pod is what you is sought after. In the seed pod is the milky fluid that contains the morphine and the codeine, and a small amount of the opiate called what's called thebaine. The juice is extracted from the unripe seed pods and dried. The opium alkaloids are extracted and then purified. In the legal pharmaceutical world, morphine and codeine are used to ease pain and spasmodic coughing. We find it in cough syrup. Thebaine is used as a retractant in pharmaceutical synthesis to produce a number of synthetic opiate compounds with a wide variety of biological effects. So thebaine is the starting point, and we use that to produce other drugs from that. These include oxycodone, oxymorphone, and nalbuphine. Okay. Naloxone, which is called Narcan. Narcan is used to treat opiate overdoses. It's useful in healing people with narcotics or alcoholic addictions to remain drug-free. And buprenorphine is useful in treating of opiate addiction because it prevents withdrawal symptoms. Okay. About 40% of the world's legal opium poppies are grown on the Australian island of Tasmania. That's where 40% of opium comes from, the legal opium. It's a big business. The industry has developed an active research program to study the different biochemical pathways for the synthesis of morphine and codeine. The pathways begin with the amino acid tyrosine. Tyrosine, remember, was the amino acid that started with for the synthesis of dopamine, or epinephrine, and norepinephrine, the neurotransmitter. Okay, same way that synthesizes dopamine and epinephrine. Okay, so tyrosine, 7 steps, reticulin, and goes to thebaine. Thebaine then gets to codeine and morphine. Okay, tyrosine is converted into reticulin. 6-reactin reticulin goes to thebaine. Modification after that converts thebaine to codeine, undergoes ester hydrolysis to produce morphine. Okay, research has found the mutant strain of the poppy cannot make morphine or codeine, but produces high levels of thebaine. And that's what we want for our research. So that's not going to produce the drugs morphine and codeine, which is what we want. So Norman, which was named for no morphine, they called it Norman, has been the most common strain of poppy growth in Tasmania since 1997, because it does not make the morphine and the codeine. The mutation that causes Norman to produce high levels of thebaine is an alteration in one of the enzymes that catalyzes the conversion of thebaine to codeine. Since it can't be converted into codeine, large amounts of thebaine accumulate in the seed pod. And that's what we want for our research. These are opium poppies, what they look like, with the different colorations of them. Okay, so the sap of the opium poppy is white. The sap of the non-morphine mutant poppy is red. So this is the Norman that we get for the thebaine right here. It's more of a reddish color. Synthetic opiates, such as naloxone, or Narcan, and buprenorphine, and others have become much more important commercially than codeine and morphine. Okay. The economic value of Norman is that it produces large amounts of the starting material for the synthesis of these synthetic opioids, as well as experimental synthesis of new drugs with unknown potential. So the thebaine is very valuable to a lot of researchers. Okay. This is, whoa, went too fast. This is naloxone, Narcan, and this is buprenorphine. You can see the similarities, see a lot of the bonds, you see the aromatic rings, the OH groups, okay? A lot of same functional groups that are on that. Okay, consider the drug formation of Suboxone, combination of buprenorphine and naloxone, so out of Narcan. It's approved by the United States in 2003 and produced by the British company Richter Benziker. This combination of opiates calms the addict's craving for opiates and poses little risk of being abused. Okay. Buprenorphine or bup works by binding to the same receptors in the brain what heroin binds to, but the drug is only partially heroin agonist, so there is no high when it bonds to it. So as a result, buprenorphine is much less addictive than drugs like methadone. Remember the methadone clinics, we use that to treat heroin addicts? Okay, methadone is addictive all on its own, and it still produces a lot of problems because methadone causes the high. So people get stuck on methadone, they'd still abuse methadone. Okay, buprenorphine has the same effect of getting people off heroin, but it doesn't have the high that methadone has. So it's being replaced in all the methadone clinics. Okay, it leaves patients much more clear-headed than methadone and makes it easier to withdraw from the drug after just a few months. I mean, methadone, people were on that for years and years and years, and the government was paying for it. Okay? And it kept people strung out on methadone. Okay, this does not have the same effects as methadone. Because addicts don't get high from Suboxone, it's much less likely than methadone to be stolen and sold illegally. You're not going to steal it if it doesn't get anybody high. No one's going to go after it. Okay. It has added advantage that its effects are longer lasting than those of methadone. So addicts need only one pill every 2 or 3 days. It lasts a lot longer. You just take a pill for it. In addition, naloxone is an opiate antagonist. It causes instant withdrawal symptoms if an addict tries to inject Suboxone for a high. So you instantly get withdrawal symptoms from it. As a result, Suboxone can be given to addicts to be taken home rather than being dispensed at clinics like methadone clinics. Okay? With all these features, Suboxone begins to sound like a miracle drug. But as with any addiction treatment, it only works if those who want to quit are willing to work with the counselors and support group to resolve the underlying problems that cause the addiction in the first place. So it's only as good as the people that are going to use it. Okay, histamine and acetylcholine. Histamine is released during an allergic response. When your body has allergic response to something, we release histamine. Benadryl. Benadryl is an antihistamine. It's used for colds and allergic responses. Okay. That was, oops, hit the button too fast. Get back to where we were here. Okay, this is Benadryl. Again, you can see the nitrogen groups in the ring, the five member ring structure. Okay, and then this is your amine group right here on the top. Acetylcholine. Acetylcholine is also a neurotransmitter. Okay, acetylcholine, which causes our muscles to contract. It's released at the neuromuscular junction. That's acetylcholine. Okay. Acetylcholine functions what's called the neuromuscular junction. Okay. Acetylcholine breaks down to choline and acetate ion. Okay. Histamine is a neurotransmitter that synthesizes many tissues by removing the carboxyl group from the amino acid histidine. Okay. It has many often annoying physiological roles. Okay. Histamine is released during your allergic response, and it causes that itchy skin, the rash associated with poison ivy or insect bites. It promotes the red, watery eyes, respiratory symptoms of hay fever. And this is histidine. This is the amino acid, and it's converted into histamine, which causes your rashes, your reactions to insect bites, to runny noses, to allergies, things like that. And again, this is your amino acid. Amino acid has your your amine group, carboxylic acid group, your hydrogen, and this is your alpha carbon right here. Okay, and it has the alpha carbon is your R group. And like I said, every amino acid has a different R group. That's what makes it, identifies between each other. Okay, so many histamines are available to counteract the symptoms of histamine release. These act by competing with histamine for the binding site to target cells. So when histamine binds to the target cells, it causes that reaction, causes the rash, causes the red eyes and all that. If you have something on there that binds to that target cell so histamine can't get to it, then you don't have that reaction. And that's an antihistamine. That's how it works. It binds or competes with the target cells that the histamine wants to bind to. Okay. If histamine cannot bind to these target cells, the allergic response stops because it can't get to them. Benadryl is an antihistamine. It's available as an ointment to inhibit the itchy rash response to allergens. It's also available as an oral medication to block the symptoms of systemic allergies by binding to those receptors. Histamine also stimulates the secretion of stomach acids. Okay? When the response occurs frequently, this can be chronic heartburn. So the reflux of stomach acid into the esophagus can result in erosion of tissues and ulcerations. So excess stomach acid may also contribute to the development of these stomach ulcers. If you get the histamine response, you get increase in stomach acid. Again, you can result in these stomach ulcerations. The drug marketed as Tagamet has proven to be an effective inhibitor of this histamine response for increasing acid stomach content. Okay? Provides relief from chronic heartburn. And this is what Tagamet looks like. Again, you see a lot of similarities to all the different medications with the ring structures and the different nitrogen molecules inside of them. Removal of the carboxyl group from glutamate. Glutamate is an amino acid. It's an alpha amino acid. Produces alpha aminobutyric acid called GABA. Okay. GABA and glycine, another amino acid, are inhibitory transmitters acting on the central nervous system. So they stop the transmission of neurons. Okay, they're inhibitory.
Alex, do you have the spoons? Oh.
Okay.
I can make it up. Yeah, I need to include spoons.
Oh, that's this one. Okay. All right, so glutamate, again, your amino acid, and alpha aminobutyric acid is what's produced from it. So this is glutamate. Again, amino acids all have the same basic compound. They have an ammonium group, they have a carboxylic acid group, a hydrogen, and all attached to an alpha carbon. Okay. What's attached to that is the R group. Every R group is different. For glutamate, it's CH2, and then carboxylic acid group. And from glutamate, you produce alpha aminobutyric acid. One class of tranquilizers, benzodiazepines, relieves aggressive behavior and anxiety. Okay. Valium. Okay, benzodiazepine. These drugs have been shown to enhance the inhibitory activity of GABA, suggesting one of the major roles played by this neurotransmitter. Acetylcholine is a neurotransmitter, as we said, with the neuromuscular junction. Functions in the neuromuscular junction, carries signals from the nerve cell to the muscle and causes the muscle to contract. It's synthesized in reaction between the quaternary ammonium ion choline and acetyl coenzyme A. Okay, we'll get into all these things in the next couple of chapters too, all these different enzymes and all the biochemical functions of it. When it's released from the nerve cell, acetylcholine binds to receptors on the surface of the muscle cell. Okay, when it binds, it stimulates the muscle to contract. Okay. Acetylcholine is then broken down to choline and acetate ion. So the acetylcholine gets released by the nerve. It travels across to the muscle, binds to the muscle, causes that muscle to contract, and then it gets broken down after that. That's how the transmission works across the junction. So acetyl, this is choline, and acetyl coenzyme A react to produce acetylcholine. So you're basically recycling these molecules. They're broken down into the acetyl and coenzyme A, and it gets recycled and used again. They're taken up by the nerve cell, where they're used to resynthesize acetylcholine, which is then stored in the nerve cell until it's needed again. So it gets released, binds to the neurotransmitter, gets broken down so it's not effective, gets absorbed as the product back into the nerve cell, and gets reassembled back into acetylcholine, so it can be used again. Nicotine is an agonist of acetylcholine, so it binds against it. An agonist is a compound that binds to the receptor for another compound and causes or enhances the biological response. Okay, so when acetylcholine binds across it, okay, the nicotine enhances the response of the acetylcholine. So it makes the muscle more sensitive, makes joints more active. Okay. By binding to acetylcholine, okay, so it's an agonist of acetylcholine. An agonist is a compound, so by binding to the acetylcholine receptors, nicotine causes the sensation of alertness and the calm many smokers experience. That's what makes nicotine so addicting. Nerve cells that respond to nicotine, we also signal nerve cells that produce dopamine. So besides just enhancing the effects of the acetylcholine, making the patient more alert, more ready for things, it also releases dopamine, which causes a satisfied feeling in the brain. Okay, dopamine responsible for the addictive property of nicotine. Inhibitors of acetylcholinesterase. Acetylcholinesterase is an enzyme that breaks down acetylcholine. If we inhibit the breakdown of acetylcholine, it doesn't break down. So the enzyme that catalyzes the breakdown of acetylcholine are used both as poisons and as drugs. I mean, think about it. If your muscle gets stimulated when this is around, and then it breaks down, and then stimulation gets relaxed. If it stops breaking down, that muscle is going to be stimulated over and over and over and over until it finally fractures or breaks down or breaks the bone or something. Okay. So if you inhibit the acetylcholinesterase, it's a poison to the body because it causes it to hurt. Or you can use a drug because the person will contract but can't contract anymore. So among the most important poisons of acetylcholinesterase are a class of compounds known as organophosphates. Okay. One of these is DIFP, diisopropyl fluorophosphate. Okay. The screen just go black. Oh, here you go. We're back again. Okay. This molecule forms a covalent bonded intermediate with the enzyme, irreversible, inhibiting its activity. So it binds to the enzyme, acetylcholinesterase, and stops it from working. So now acetylcholine cannot be broken down into acetyl and choline. So it continues to work. This is diisopropyl fluorophosphate. It's organic phosphate. Okay. The enzyme is unable to break down the acetylcholine, and nerve transmission continues, resulting in muscle spasms. And death may occur as a result of a laryngospasm. Your throat spasms so hard it shuts down and it doesn't open back up again. Okay. Antidotes for poisoning by organophosphates may include many insecticides, and nerve gases have been developed. So organophosphates are used in the insecticides. They've been used as nerve gases during war. And we developed several antidotes for that. The antidotes work by reversing the effects of the inhibitor. Okay, so where the inhibitor is binding to the acetylcholinesterase, we work on reversing that effect, either by remodifying the structure of the enzyme or by modifying it to the point where the inhibitor can't bind to it anymore. One of these antidotes is called PAM, pyridine aldoxine methadide. This molecule displaces the organic group from the active site of the enzyme, alleviating the effects of the poison. So it doesn't bind to the enzyme is not affected, the enzyme can continue to break down the acetylcholinesterase so the muscle doesn't go into spasm and keep contracting. And this is what PAM looks like, very simple compound. Okay. Succinylcholine is another one, it's a competitive inhibitor of acetylcholine, which is used as a muscle relaxant during surgery. Okay. Acetylcholine binds to it. So acetylcholine binds to the receptor, the muscle contracts. Succinylcholine binds to that same receptor, but it doesn't cause contraction. It binds to the receptor and blocks it from acetylcholine binding to it. So you get no contraction and you basically block the receptor. Okay? So competitive inhibition occurs because the two molecules have structures so similar that both can bind to the acetylcholine receptor. And the acetylcholine triggers the muscle to contract. The succinylcholine does not trigger the muscle to contract. It just binds to the receptor. When administering a patient, there's more succinylcholine than acetylcholine in the synapse. So the acetylcholine binds, so more succinylcholine binds to the receptor. Therefore, the patient can't move because it becomes paralyzed. And that's what you want for a surgical procedure. Now, you have to understand too, when you're using this, succinylcholine paralyzes your patient, but it does not do anything for analgesic properties. The patient can still feel everything you do. They just can't move. And there's been several horror movies based upon that fact. Been developed. It cannot stimulate muscle contractions, since acetylcholine causes muscles to relax and they just can't move. You basically paralyze a person. Normal muscle contraction resumes when the drug is no longer administered. It gets flushed out of the system with time, and then the acetylcholine takes back over. Okay? So this is acetylcholine, and this is succinylcholine. And you see some similarities there. They look like a molecule just flipped over on itself and doubled. So very similar molecular structures were at the bonding site. Nitric oxide and glutamate. Nitric oxide has many physiological functions. Okay, it's able to act as a neurotransmitter. Nitric oxide is synthesized in many areas of the brain from the amino acid arginine. Research says that nitric oxide works in conjunction with another neurotransmitter, the amino acid glutamate. Okay. Glutamate released from one nerve cell binds to receptors on its target cell. This triggers a target cell to produce nitric oxide, which then diffuses back to the original nerve cell. Okay. This NO signal the cell to release more glutamate, thus stimulate the neural pathway even further. So it's a feedback loop. Okay, creating more and more and more as it goes along through the system. It's a positive feedback loop. It is thought that this nitric oxide glutamate mechanism is involved in learning and the formation of memories. Because when the nerves can form, they can store something and then go back and regenerate. That way you're regenerating the pathway so you can pull that memory back up again. All right, summary for this chapter. What we talked about: reduction of a nitric compound produces an aromatic primary amine, adding hydrogen. Okay, we talked about an amide, reduction of an amide to produce an amine. So these are preparation of amines. You have amine reacts with water. Okay, give you a hydroxide ion and alkyl ammonium ion, depending what the R group is. Okay. Amine in the presence of acid forms an alkyl ammonium salt. Remember the H, this goes here, forms a positive charge, these are chlorine minus, and then these two combine. Acid, chloride, and ammonia, or an amine, okay, produces, that's what we produce an amine. These are acid chloride, and it took two molecular equivalents of the nitrogen compound to form the amide. Okay, and it forms the ammonium chloride salt or the alkyl ammonium chloride. Here's the same thing with acid anhydride. Acid anhydride reacts with two molar equivalents of the ammonia of the nitrogen source, and it's going to produce an amide, okay, and the carboxylic acid salt. The difference between adding an amide with a strong acid or a strong base. When you add it to a strong acid, you get the carboxylic acid being reformed, and you get the ammonium with the extra hydrogen from the acid. When you take the amine in a strong base, you get the carboxylic acid salt, so that the hydrogen's been donated to the amine. Okay, so you get the minus and the Na plus, and then you get the amine being formed as the byproduct. So you got to remember that between a strong acid and a strong base, what happens with an amide. Okay. So we have nitro compounds, go to amines. Amides can go to amines, and amines can go basicity with water, goes to the alcohol hydroxide, neutralization with acid, goes to the alkyl ammonium salt. With an amide, they're formed by the acid chloride and the amine. It takes two of these amines motor codes to react. And they're also formed by acid anhydrides. Okay, there's two ways to form amides: the acid chloride and the acid anhydrides. Okay. Hydrolysis, it's a base. You get the carboxylic anion, okay, and the amine. If it's an acid, you get the carboxylic acid and the alkyl ammonium salt. Perfect. All right, so amines, preparation from the nitric compounds and amides, basic environment, basic reaction, and neutralization occurs. Remember the hemiacetyl and acetyl groups, hemiketyl and ketyl groups. Amides are formed by preparation is acid chloride or acid anhydride. amine or ammonia. And hydrolysis, amide plus acid produces the carboxylic acid and the alkyl ammonium ion. The amide plus base produces the carboxylic acid salt and an amine. And there's a summary of all that we talked about with the different reactions.